participants here. Still quite a few coming on. It's exciting. We'll just let a few more people come on. We'll give everyone about 1 minute. Okay. Well, thank you everyone so much for joining us today. I'm Sarah Hardwick, Aptera's Chief Marketing Officer, and I'm pleased to be here today to introduce our Chief Technology Officer, Nathan Armstrong. But before we begin, we just have too much exciting stuff happening here at Aptera. I would love to share just a few quick updates with you. We've had so much cool stuff that's happening. Just a few highlights to start off our presentation today. So we are not there yet, but we are quickly approaching 10,000 reservation holders, which is just absolutely an incredible number for us. We are so amazed and appreciative of all the outpouring of support that we've been seeing. We also have 150 plus brand ambassadors who are joining us from countries. We have actually now 84 countries around the world who have reservation holders. It's so exciting. And while the pandemic has definitely impacted some companies that are within our supply chain, we are absolutely still on target to deliver our first vehicles by the end of the year. And a couple other exciting points of note, if you haven't watched our original launch video, it actually has over 1.3 million organic views on YouTube. And if you didn't see us in the climate change section of the Washington Post, make sure that you have a chance to check us out. And coming up soon, we have some great announcements. We'll be launching a new website. And for all of you reservation holders, it will allow you to configure your vehicle in real time and find out more about your Aptera, see when your Aptera will be estimated to be delivered, and all sorts of other exciting, cool features on our website there. And then lastly, we do intend to continue to open up a new round of investment opportunity in the coming months, and we'll be sharing more with that shortly. So our topic for today is aerodynamics. And why is aerodynamics so important? Well, it is the key to efficiency. So as you guys know, our founders have been focused ruthlessly on efficiency from the very beginning. And so these are some cool pictures from a very long time ago, as you can see by our young and handsome founders there. They were actually focused and really driven towards our mission of efficiency, the entire reason for starting Aptera. And their vision, which is what we're really on a path to achieving now, is to create a fleet of vehicles that are not only efficient, but lightweight, safe, and fun to drive, which is pretty much what we've done. We are so excited. We're so close to achieving our goal. This is an image of last week from Aptera being tested at the track, which was, for myself personally, I actually had the chance to take Aptera for a test drive. And it was, honestly, guys, it was unlike anything that I have ever experienced. It was so cool. It was just really thrilling, and I can't wait for all of you guys out there to have that same feeling. So no one knows that feeling better than Nathan Armstrong, who is our Chief Technology Officer. He's been around since the beginning, and he has seen that evolution of the company. So we're going to be hearing a little bit from him. He has some great experience. He's a mechanical engineer. He's worked with some of the top EV brands in the industry, and he actually was an engineer on the International Space Station. So Nathan's going to be leading us in a discussion today about some key areas of our vehicle, including Aptera's ability to be lightweight, aerodynamic, our composites, and then also safety. So we will be doing a live Q&A afterwards, so feel free to pop your questions in the chat there. But at this point, I'm going to start sharing, and I'm going to let Nathan take it away.
All right. Well, hello, everybody out there. Hello, Mom. Thank you, Sarah. Was it better than chocolate was one of the questions there. I think we should just dive into that one, Sarah.
I think, why don't you just go ahead and start and just tell us a little.
Sure. Yes, it is better than chocolate. So today we're talking about aerodynamics, we're talking about safety, we're talking about composites, and we're talking about the goal to strive for perfection in efficiency. And so you want to start with aerodynamics. So I guess, as everybody kind of knows, I mean, one of the goals of Aptera from the very beginning was to demonstrate like an extreme in aerodynamics, right? So the most aerodynamic shape possible while containing two people safely was the original ethos. And when we started looking at the numbers, and the original shape came from Steve's kind of vision of a shark swimming on the ocean floor, was where the original kind of shape came from. And when we started running simulations on this shape way back in 2006, 2005, we realized that the net gain that we were seeing over like current vehicles was such a paradigm shift in efficiency that they really drove the program forwards, because we were as aerodynamic as the windshield wipers on a pickup truck at the time. And one of the references was the same as a 12-inch cube driving down the street. And when you compare that to a current vehicle, you realize that we really, there's a huge amount of gains to be had in the design of vehicles still. So that was really one of the original drivers that kept us to keep going down this path of trying to get the ultimate aerodynamic shape while keeping you safely going down the road. So.
That's great. I think we can just, are there specifics you want to talk about, Nathan? I can just kind of dive into some of the questions, but I think I know kind of one question specifically just that popped up and I saw a couple times already is stability. So can you talk a little bit, speak a little bit more about kind of aerodynamics and stability specifically?
Well, stability when it comes to aerodynamics is, it works in our favor in all cases. Side wings, headwind, any kind of like wind obviously just blows around the vehicle because of the shape of the vehicle. So we're not subject to the same kind of crosswind forces as most vehicles. But stability is mostly based on where your mass is placed. And in a three-wheel vehicle, there's well-known equations how you achieve this. A little bit of stability control in there, and you basically got a very, very stable vehicle. It's an analogy to the three-legged bar stool kind of a thing. It's no less stable than a four-legged bar stool. So the current vehicle out of the drag strip doing the moose test and doing all the tests is performing great. So stability-wise, it's a really strong platform, and it feels very stable. Like when you drive the car, it doesn't feel like driving a three-wheeler. It feels like driving a just kind of an interesting normal car.
So one of the questions, I'm going to put my video on here. One of the questions that we see here is specific to counter efficiency. Specifically, let's see, we're asking these some great specific technical questions, but talking about the body strength specific to the roof. Is the body strength, would the body strength be enough to get rid of the roof is one question that just came through.
No, it wouldn't. No. The whole vehicle is basically like a motorcycle helmet. It's one big stressed skin composite monocoque that we fill with foam, and the whole thing becomes a structural unit at the end of the assembly. And the roof is definitely integral into keeping that whole thing stiff.
Yeah. Maybe I think just kind of the key areas that we talked about that you were going to dive into. Why don't we talk a little bit just about like Aptera's ability to be lightweight? So lightweight yet strong. So tell us a little bit more about, how can this be achieved? We've heard about Formula One race cars. We've heard a little bit about, all these aerodynamics. So tell us about how it's possible for Aptera to be so lightweight yet so strong.
So that all came from developments in the composite industry that happened during the mid-90s, early 2000s. When vacuum resin infusion and high-performance resins started coming into the market, and composites took a really big leap in what they were able to do, and especially on the production side. Like a whole bunch of new techniques were kind of invented and brought into the market that really gave composites the jump from like hot tubs and like that kind of shower stall thing to like high-performance composites. Not quite aerospace level, we're not talking autoclave level, we're talking still vacuum resin infusion, but the still performance here was so close to where aerospace was that we were able to get super high performance composites with relatively low upfront investment compared to typical aircraft tooling. So that really gave us the ability to design structures that we weren't able to before. And the goal of these structures was primarily safety. Because composite structure isn't like a metal structure. When it's impacted, it caves in, absorbs the energy, but then goes back to its original shape. And we saw this on the very first car when we tested the roof crush, and we pushed it down with a hydraulic ram, and we took the ram off, and the whole roof just went pop, and like popped back to its original shape, and we all just it was one of those moments when you're like, this is a huge paradigm shift in safety, because if we can tailor the composite to absorb the energy how and where we want it to, and then return to its original shape, we've got a massive gain in safety. So that was a primary factor, and the lightweightness of composites just comes, it's like a byproduct almost, just through the nature of the material and how you do the construction. You went with very lightweight structures, but extremely safe. Like so safe, like we just couldn't believe it when we were doing the original tests. Like I think we beat every world record for roof crush test and side impact test and everything. Again, it was one of those things early on in the program that spurred us to continue down this path of really perfecting the composites and the structure of the vehicle.
Can you tell us, Nathan, what is the actual weight of the vehicle?
I think the body tub itself, the structure itself, is 190 pounds. And then the vehicle fully built out is less than 1,800 at the minute. But we're trying to get it a little bit lower than that. We're trying to get it down to, as low as we can kind of thing. But it's still extremely lightweight. And one of the interesting things we're playing around with now is that because we've got in-wheel motors, and there's a question down here about sprung and unsprung weight, because we've got more sprung weight now and less unsprung weight, we're having to do very clever things with suspension design and spring design, that kind of stuff to compensate. But the in-wheel motor is going to be a very interesting thing for people to experience and to drive a vehicle with in-wheel motors, because the torque application it feels different than a normal car, and it's going to be exciting for people to drive an in-wheel motor vehicle. I think it's going to be a paradigm shift as well.
Thank you. One question that came in, at what speed does aerodynamics become significant?
35, 45 miles an hour, somewhere in there. 55, it becomes significant. 65, it really makes a difference. 85, it's massive. Anything below 35, it's still significant, but it's not as significant.
Yeah. Okay, great. So what materials, can you give a little more on the materials of the composites that our production vehicles will be made of? I know you may have some samples hiding back there, some visual displays that you might be able to show us there.
I do, yeah. No, this is an interesting part of the project, because when you start talking about epoxy-based composites, you start talking about things that potentially could last indefinitely, like literally, hundreds and hundreds and hundreds of years kind of thing. Within the company, part of the deep-rooted philosophy is that we want to make things that last as long as we possibly can. Like, we would love these Aptera to be passed down to people's grandchildren, and basically just refreshed and upgraded over time kind of thing. But there's no reason. I mean, the body is hail-proof, it's dent-proof. I mean, there's no reason it should ever degrade. So the main body itself is just glass fiber reinforced epoxy. There's nothing really magic about it. What is special is that the epoxies now are way more high performance than they were 5-10 years ago, and the fiberglass is the same as it has been, but it's still good material. Like on the Boeing 787, it's all used on the wing nacelles for the flexibility of the wings. But how we design the parts, bond them together, do the foam fill, and build the structure with the fiberglass is really the secret sauce. So that's the body. And then the interior and the exterior panels that we're expecting to have to be replaced over time. So panels that are going to get damaged and need to get replaced. This is where this stuff comes in. So this is the accumulation of 14 years' work to develop a natural fiber composite material. And this is a hemp material. It's grown in Canada, it's processed in Europe, and then we bring it back here for manufacturing. But this is 100% natural, obviously. Required no processing to get to this point, apart from 1,000-year-old technology to remove the fiber of the plant and weave it using, again, 1,000-year-old technology. But what we're finding is that when you configure natural fibers in a manner like you would a regular composite, the strength benefits are incredible. So we're seeing that this actually is becoming a more high-performance material than we were expecting. And the long-term vision is there are resins on the market now that act like epoxy resins, that have the same performance as epoxy resins, but are 100% natural material-based and are 100% biodegradable. So they last above ground indefinitely until you bury them, and then they basically just dissolve. So if we had a natural fiber-based composite with a resin that was biodegradable, we would have high-performance parts that would be 100% natural and biodegradable. So we're thinking that the replacement panels, interior panels, parts that are not so structural can be used out of this material and be designed to be replaced. And then the main body itself will be designed to last indefinitely kind of thing. So So the natural fiber composites is very exciting for us. It's an area I think we're going to demonstrate that. Like it's been done before, like the BMW i3 used it on the dashboard, but it was just a pad, it wasn't structural. And we're saying that we think we can actually now make semi-structural panels from the natural fiber material. We wouldn't go full structure, but like this accent and like the outside panels could be possibly just made from natural fiber. So that's for me personally is like, that's huge. That's a great one. So
Yeah.
yeah.
That's great. Thank you so much. So in regards to our composites, can you talk a little bit about in the event of a collision, are there designed crumple zones? How do the composites behave in that type of situation?
Yeah, well, of course, we've got 6 or 7 different scenarios that we have to look at. We've got front, side, rollover, rear, rear three-quarter, front three-quarter. And in every scenario, the vehicle is designed to absorb the impact in a specific way. And again, because of composites, like with metal, you can't tailor metal specifically down to like, well, you can get down to the grain structure, but not really. Like you can get down to wall thicknesses and ribs, that kind of stuff. With composites, you can literally place the fiber specifically where you want to see the loads transmitted to. And you can tailor it to flex in one direction or not another. You can do all sorts of things with it. So the body is designed to absorb impact in every scenario that we can imagine. And then, like we say, return back to its original form. Which is massive. The front of the vehicle has a metal subframe, so we have the composite tub stops at the firewall. There's a metal subframe in front. That whole thing is designed to collapse, absorb energy, before it gets into the passenger compartment. And in a normal 45-mile-an-hour collision, the passenger compartment shouldn't get damaged at all. Like that should be completely savable for the next. Just change the front end. Side impact is great. Rollover, like I say, we're at like 6 times vehicle weight on the last vehicle test we did. So rollover, I think the vehicle probably won't do anything. So anyway, we're excited to test this new body structure. We've improved it a lot over the last vehicle. There's more roof structure. We've eliminated some metal that we had in the very first car that we didn't like, so we got rid of that. And we've got full composite now, and pretty soon we're going to be building the jig again and crushing the things and seeing what kind of results we get this time. But if it's anything like the first car again, it's going to be record-setting performance.
Thank you. Thank you. Couple of questions here regarding, and this is just kind of taking a step back, but the aerodynamic shape, how does that impact kind of the classification of Aptera? How do you see Aptera in the landscape of other vehicles is one of the questions here. So where do we fit?
Classification-wise, well, it's an autocycle in the US, as we know, right? So it's a motorcycle essentially, but autocycle is one of these interesting classifications that kind of in between. So if that's the question, it was just we're autocycle.
Yeah.
Yeah.
I think that's probably enough for right now. We have quite a few of our fans online today who are interested in the camping package, the off-road package, and wondering how that might potentially impact aerodynamics. Is there anything that you can speak around our plans for that and how that might potentially influence the aerodynamics of the vehicle?
I don't know how much I can say on that. There is a conversation happening and a team looking at doing adaptive suspension, like adaptive high suspension, right? So, airbag would be one way, mechanical we do another way. But for the camping package, the off-road package, the thought is that you actually could raise the vehicle a couple of inches, right? So that'd be something there. And then if we had that suspension, you could also lower the vehicle at high speeds, right? So that would be something else that we're investigating that we're not putting out there yet. Like it's a very expensive package to do that. And overall in the cost of the vehicle, it would be quite an impact. But if we could have adaptive suspension, of course, for off-roading, that would be neat. So, but of course, the vehicle's so light, and if you've got 3-wheel drive, it's going to be tremendously capable off-road, strangely enough. Like, I bet we'll see some people off-roading these things and doing crazy things with them, right? So.
Yeah, and I think that brings up a good point. There have been a couple questions asking how far along are we in testing? How finalized are we? Have we received all of the correct certifications? And so maybe if you can just explain a little bit, where we're at, because we are at a point where we're testing a lot of things, looking at it, doing a lot of analysis, looking at how things are impacting aerodynamics. So can you kind of explain a little bit where we're at? And that does leave some room open for some potential changes to be made to the vehicle, probably or potentially before we even take it to market. So any thought on that?
Well, as you know, the state of the vehicle at the moment is the black one that you see around at the moment. There's a whole series of vehicles being built based on that design, which is a design we started back in 2019. Since we evaluated that vehicle and did the testing on the vehicle, we've made some changes to the body. We've made a bit more room for batteries, made a bit more room for the occupants. We've actually improved the aerodynamics slightly, which was a huge thing for us. But that new design is now going into, well, it's already into the production engineering cycle. We are a decent ways through that. We're going to be releasing tools in the next month. We're going to be hustling to make probably 10 vehicles through the summer, and then they go into testing, and we've got all sorts of testing planned. And then by the end of the year, like everyone knows, we're hoping to have the design stable. We're hoping to have the prototypes finished. We're hoping to have certification in place. And we're hoping to get going on production beginning of next year kind of thing. So as far as certification, I believe everything is understood for the US. I think all certification-wise, we're good. We're aiming to meet all certification for passenger vehicle specifications, which is a fairly lofty goal. There are some things that we're trying, like we might be looking at polycarbonate windows to save weight, which isn't actually something, I don't think it's allowed in automotive at the minute, but it is allowed in a motorcycle. So we might be using the motorcycle regulations to our advantage if we can save weight, obviously without reducing safety, but that would be an area that if we could save weight, we would. Like I say, we're trying to meet passenger vehicle specifications, safety specifications,
Great.
Yeah.
We have a lot of technical questions specifically around the composite. So someone's asking about the epoxy resin. How does that epoxy resin, how long does it take to cure, and how does that affect the ability of our vehicle to move into production?
Oh goodness. Well, there's UV cure epoxy, which basically uses like a dentist thing, which flashes UV light and it cures in a few minutes. We're working with a group that have a flash cure system where the turnaround time is 3 to 5 minutes per part in the tool. So, we have to be in that kind of range. Typically automotive, you want a part per minute. Our takt time is a bit longer, so if we have a part per 5 minutes, like we're probably fine kind of thing, but that's our goal for all the turnaround on these tools. So, it's very exciting.
Yeah. Okay. So one question was in response to your statement that we form the shell using similar methods as fiberglass boat hull production. So these can be expensive to repair. Can you talk a little bit about how, repairability of our composite shell, how will that work?
It sort of isn't. It's sort of like you could, right? Like you could repair the body, but it's kind of like a motorcycle helmet. Right, like once you've cracked it with a composite structure, you really don't know what internal damage you have, so you typically just replace the helmet. The monocoque of the vehicle, like I say, it's not complicated. To tear a vehicle down and rebuild it can be done in a few hours. So if you did damage your monocoque, the idea would be you would just replace it. You keep all the good parts on your vehicle and you just put them on a new monocoque.
Great. Another question around the long life expectancy of the body. So given that we expect it to last a significant time, is our body cavity that holds the battery package designed to accommodate future battery configurations as that technology evolves?
Oh my goodness, yeah. I mean, we're seeing battery technology now. The big gains that we're seeing is in size, like density versus size. So the battery pack we have now is the biggest, I think, that we're ever going to need it to be. And it's so big right now. It's crazy. The whole belly of the car is all batteries. And it looks like with the new technology that's talking 3 to 5 years from now, that's going to be half the size with the same density. I think the battery is going to end up getting quite a bit smaller. Obviously, if the density improves versus to weight to size ratio, then we can just get more range with the same size battery. But at the moment, we've got enough space to pack. Like so many batteries, it's outrageous how they're contained all in the belly pan.
That's great. Okay, a couple questions regarding heat dissipation and the flexibility, the durability of our body over time. So can you talk a little bit about how heat acts with our composites and how it dissipates, how it potentially might impact our body structure?
Heat doesn't affect it. It's cured at such a high temperature that we don't even get close to that with normal everyday temperatures kind of thing. I've seen some questions about hazing, like on the polycarbonate. We're doing coatings on the polycarbonate to avoid that. We put UV inhibitors in the fiberglass resin, so that it doesn't degrade over time as well. And then, of course, the goal for all these cars is going to be a paint film wrap versus like traditional kind of paint. And then the paint film as well has additional protection. And of course, if you just scratch your car, you just change the paint film then, right? That becomes part of that whole thing. So, and that comes down to kind of part of the ecological kind of footprint too. Like painting is a very dirty process, and to set up a paint plant is a real, that's not a nice thing. So the paint film and how we do that automatically and how we kind of automate the process of applying the paint film is going to be something we.
Yeah, and that's going to be an exciting thing we'll be announcing for you, our reservation holders, at some point soon. We'll be releasing what those options are, and we have some really great solutions that we have come up with for you. So we're very excited about that. Okay, question regarding opening the windows. We have a specific kind of, half window there. Can you talk a little bit about that? There are some questions regarding how that might impact the aerodynamics.
Well, that's that actually, when we first started working on this car, when you design a car, the very first thing you design is the glass drop. Right? You design a barrel so that the glass drops into the door. That's how you start a car design. And when the Aptera was designed, it was designed as an aerodynamic form primarily. And then when we were like, hey, how do we get the glass to go down? And you start looking at the because it's not a cylinder, right? It's a very complex curve to the body to it. So as the glass drops, it goes through this weird corkscrew kind of motion. It causes all sorts of headaches. That's why we could only do half the window, right? Is because the curvature of the window would not allow the glass to drop inside the door. It just wouldn't go. So the glass we have, the door we have now is big enough to get a soda can through kind of thing. Drive-through window would be fine kind of thing. Aerodynamically, it shouldn't make a lot of, it would make some drag at high speeds, but at low speeds with the window open, we've got decent flow over that panel that it's not going to be too noisy in the car or cause too much drag kind of thing. But yeah, those regular window goes up and down.
Okay, great. Okay, now can you elaborate a little bit? I mentioned that Aptera draws inspiration from Formula One race cars. We have a special safety cell that we've engineered. Can you talk a little bit more about where that inspiration comes from? What that means? Can you elaborate on that for one of our participants?
Well, yeah, I think everybody's seen Formula One cars in a crash recently, right? And everyone's seen how the tub performs, right? I mean that it's a great demonstration of what composites can do when they're designed and used properly. I mean, they're tremendously safe. Not only do they, like I say, absorb the impact and bounce back, but because they are lightweight, there's not much mass there to have to absorb the energy anyway. These things being super safe. The inspiration from the composite goes back to Lotus back in the 60s with the Lotus Elise, which was the first all-composite road car and wasn't copied until modern supercars, right? But modern supercars at the minute have kind of the niche on composite tubs and composite structures. The BMW i3 and the i8 had composite structures. So that was really a first foray of a major automaker into like a passenger vehicle with a composite structure. But again, I believe it was demonstrated very well in those vehicles. I don't think there's been any issues. So we're just kind of carrying down that path. It's an evolution from DuPont back in the 40s through where we are today with composites. And like I say, we still see a lot of low-hanging fruit. We still see a lot of improvements to be made. We're still seeing a lot of new tooling techniques coming out that people are inventing. That's quite exciting too. So, yeah.
Thank you. One question is around what type of simulations are we running? And I know I've seen some really cool graphics with, showing the airflow, and we actually showed some of those really briefly during the introduction section here. So can you talk a little bit about, I know in the old days, a decade ago, it took a lot longer when you would make changes to the vehicle to look and design to see how that would impact the aerodynamics. But I understand now it's, a radically transformed process that allows us to get input, nearly immediately. So can you walk through what that process looks like?
Like if you go back to back when we did the first car, we had Miles Wheeler, who was our aerodynamicist, did the virtual study on the car, and you can do this thing where you glue little pieces of string all over the car, and you see how the strings flap. And back in the day, that's what they would do. They would glue string on the car, go drive it with another car next to it, and video what the little pieces of strings were doing. So you can run that as a virtual test in the software we have. So he ran that test, and he had one little piece of string, like by your shoulder, on the back of the car that was flapping. And we were like, that's strange. So we actually did it. We went out to the track and we glued pieces of string on the car and we drove the car, and that one little piece of string was flapping. Like the simulation was so accurate it got down to like that level of like, and we were just blown away by this. Like we're like, well, the simulation software is like so incredible, and the Aptera is such a beautiful case for the software, because software normally is challenged with very unaerodynamic cases that you're having to improve, whereas with the Aptera is you get these beautiful laminar results, and as you adjust the simulations on the surfaces, you see how the laminar flow changes. Like it's just beautiful. So we're doing a whole bunch of aerodynamic simulations. Actually, they're finished now. The new body is set, and everything's finished there. There's composite, crash simulations that we're doing. There's mechanical stability simulations using software called Atoms to do that. That is because all driving forces and all that kind of simulations. The wheel motor company we're working with are running simulations as well to get us the best traction control and stability control software developed. So, but I'm a big fan of real world testing. That's what I'm excited for. Is actually get some of these cars and go, do like crazy things with them, and see if we can break them. So.
That is exciting. One question is around surface treatments, and have you explored any surface type treatments to increase aerodynamics, like a shark skin? I think he mentioned.
There was something about that. There was somebody who came out with a film that had a nano, like a golf ball kind of a dimple thing. I think we actually tested it on the first car, and I don't think it actually made any difference. And I think on the first car too, we actually experimented with like dimples on things like golf balls too, like on the inside of the fenders. I think we had down at the very beginning, but it didn't seem to make a lot of difference. The car's so efficient as it is, those little gains don't really give you a lot. So.
Yeah.